Analyzing the graph of f of xy equals xy, subject to the constraint g of xy equals x squared plus y squared minus 4. In the first place, we might consider understanding what the three-dimensional graph of the f of x equals xy function looks like. It's a hyperboloid, and you can work out what it looks like. We've looked at this function in various ways, and we should have a pretty good idea of what the three-dimensional graph of this function looks like. Now, the two-dimensional constraint is that g of xy is 0, where g of xy is x squared plus y squared minus 4. Setting that equal to 0, we get the equation of a circle, centered at the origin, radius 2. Okay. We know that this function is going to have, if this function has relative maxima and minima, any relative max or min is going to occur when, as we move along this curve, the value of f neither increases nor decreases at the given point, which means, for reasons that we kind of outline here, that del f and del g have to be parallel, so that del f is some multiple lambda of del g. Okay, now without going too far into the geometry of it, simply means that del g being perpendicular to the curve, and I've drawn del g vectors at representative points along the curve, and the magnitudes of these vectors, I didn't draw any magnitudes, we didn't analyze the magnitudes, and you can do that yourself if you want to draw these with appropriate magnitudes. But the purple vectors are the del g vectors at the various points, always perpendicular to the curve. Always perpendicular, always perpendicular to the curve. Meaning that all your del g's are perpendicular to the unit tangent vectors. Okay? Unit tangent vector at any point being your direction of motion. And the only way you have zero rate of change of the function f at a point is if del f is also perpendicular to the unit tangent vector. So, and that's because del f would then have zero component in the direction of the unit tangent vector, i.e. in the direction of motion. Del f being the direction of maximum increase, the unit tangent vector would then be the direction in which the function f is not changing. Okay, well, that gives us this. And I've drawn del f vectors for this function. Here, 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 and here. The directions are right. The magnitudes, again, are not really representative. Okay, taking del f equal lambda del g, I find that the y component is going to be lambda times, the I component is going to be lambda times the I component here, giving us this equation. Y equals 2 lambda x means negative 2 lambda x plus y equals 0. And j component equal j component gives us this equation, giving us x equals y over 2 lambda, y equals x over 2 lambda. Possible if and only if lambda equals plus or minus 1. You can work out the details of that. Which happens then only if y equals x or y equals negative x. If you look at the picture on the circle, you see that the del f and del g line up here, 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 and here. Now you look back at the function, look at your del f and del g, and convince yourself that they do line up at these points, and these points agree with y equals x or y equals negative x. At this point, y equals x, everything lines up. At this point, y equals negative x, everything lines up. Y equals x here, everything lines up. Y equals negative x here, everything lines up. So that these points will be your essentially critical points, your points at which the function is not changing as you move along the curve. The value of f is not changing as you move along the curve g equals 0. And then we simply evaluate the function at these points and find that f is 2 here, it's negative 2 here, 2 here, negative 2 here. Incidentally, f is also 0 on any point that's on one of the coordinate axes. So we now have a picture. We go from F goes from 0 to 2, then back down to 0, to -2, to 0, to 2, to 0, to -2, into 0 as we move around the circle.